Okay, so let's start with the problems. So today mainly we will discuss on separation axioms. Okay, so and maybe on the next session we will discuss about something on bicategory theorem. But I think there are plenty of example exercises are left for you, and I think those are important for your exam, means upcoming minor exam. And that's why I thought I should have solved this in the during the class. Yes, in this session. Okay, so let's start with this one. How do we do it? Can you see my screen?
Yes, sir.
Yes. Yeah. So okay, so let's solve quickly this first 2 or 3 problems, and then we have to do something on the exercises by from the book by Alipintas. Okay. So can you please quickly give the example, which is T1 but not Hausdorff?
Cofinite topology.
It is not working. I don't know. X, where X is
Infinite.
X is infinite, and with cofinite topology, right? What about this one? First countable and T1 implies T2. Take X as n. Okay, the countable set. This, of course, that n should be that space X should be infinite, but it has to be countable infinite. So if it is countable infinite, and if you consider the cofinite topology here, then you can see that this space is first countable. It is T1, but it's not T2. Okay. So I leave it for you to verify that it is T1 and first countable, and that the space is not T2 is obvious, right? Okay. So what about this one? When so if all these collections means all these spaces are Hausdorff or T2, then the product space is also T2, right? How? 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 Take X not equal to Y from the product, or I equal to 1 to n, and this is xi. This should be xi. I forgot to write this xi. Then what can you say from here? This x will be of the form x1, x2 up to xn, right? And y will be of the form y1, y2 up to yn, where xi comma yi belongs to xi. Then what can we say when these two are not equal? Hey, please respond.
X7 not equal to y1 and x2 not equal to y2, and so on.
For all means x not equal to I
There
means for
exists, sir.
There
yes,
is
At
one.
least
there
one.
exists. There exists some I, or say some I naught, such that x I naught not equal to y I naught, right? And since these two elements are from x capital X I naught. Now this is Hausdorff space or T2 space, and these two are distinct elements, so they are exist U and V open in xi naught such that xi naught belongs to U, yi naught belongs to V, and U intersection V is empty. Right. Then what should be your final open sets which contains x and y? So say U or okay. So let's give the name as UI1 here or I0 here. Okay. VI0 here. So UI0, VI0 here I0. I'm just fixing the index. Now you take U. What should be your U? Its choice. This is yes x1 cross x2 cross up to a cross x I naught minus 1 cross u I naught cross x u sorry x I naught plus 1 cross up to xn. Okay, or simply you can say product of xi I not equal to I naught cross u I naught. Okay, and then similarly what will be your v? Your v will be I not equal to I not xi cross v I not, right? Yes. Could you verify u intersection v is empty? Is it? Yes, please response. Actually, I have to. Otherwise,
Yes, sir.
you will miss something. So please respond quickly. So yes, it is yes. Because here, if there are some element, then that element will have the ith component will be in both ui and vi, and this will contradict this hypothesis, right? Okay. So done. Now, if a space is separated by continuous function, then the space is T2, right? Can you do that? Means if f, so what do we mean by separated by a continuous function? Means for any two element, any x not equal to y, there exists a function x2001 such that fx equal to 0 and foy equal to 1, right? What happened in those? Right?
Yes, sir.
Yes. So then for these two element which are not equal, what should be the open sets containing this and what should be the disjoint open sets? It is simply f inverse 0 comma say 1/3. This is our u and your view can be you will be f inverse say 2/3 comma 1, right? So verify that these two are open sets and contains x is in is y is in this and these two are disjoint. Okay, and u intersection v is equal to 5. See, I am quickly solving first 3 or 4 problems because we have some difficult because these are relatively easy than the next problem, so which I am thinking to solve. Okay, so this one. So the projection map is not closed. This need not be closed. So can you give an example, quick example? Yes. X-axis, y-axis, and the annual and the function is okay. Let me okay. So let's say our x1 as r and both as x2. Okay, means we are in R2, And so what we have to prove is that if we are able to prove that there is some continuous function, sorry, there is some closed subset of R, or there is some closed subset of R2 such that pi 1 of R2, sorry, pi 1, so A, we have to find out is a closed S in R2 such that pi 1 S or pi 2 of S is not closed, right? This one we have to prove. So what should be your suitable S? Can you give an example?
X,
S
y,
is x comma 1 by x.
y equals to 1 by x, x greater than 0.
Yes, x comma 1 by x such that x greater than 0, right? Means this one. So this one, this curve, right? If you take the projection, then the image will be this one up to infinity here, and this is not closed, right? Therefore, pi 1 is not a closed map. Fine. Okay. Now let's move to the problems on your book by Alep Printers. Okay. Huh. Again, this problem is from metric space, right? And you have done your metric space in the last semester. Now tell me, so how do you solve this one? Just give me the idea. Okay, so let's first prove the forward direction. Means so suppose d of x comma a equal to 0. Okay, you have to prove that x belongs to a closure, right? Where x is an element from X. So what you have to take to prove that X is an A closure? You have to take a neighborhood of X, right? In particular, take a basic open set. Or so let epsilon greater than 0. Okay, and you have to find that B, if we consider that open ball, X comma epsilon, if this intersection A is non-empty basically. So how do you prove? This is because infimum of this one. So d of x comma a such that a belongs to a is 0. This is equal to 0 and you have epsilon a positive number. So then what can you say from the definition of infimum? There exist. Yes, quickly.
There exists A1 belongs to A such that
A1 belongs to A such that
d of x comma A1.
d of x comma A1 is less than epsilon. Right? So have we got this one non-empty? Okay, sorry, non-empty. Have we got this one? Yes, right? Because this implies your A1 belongs to B of x comma
Dx
epsilon.
epsilon.
Yes. But this A1 is also in A, so it is in intersection. And therefore this set is non-empty. Right? So we are done. Means x belongs to A closure. Now let's prove the reverse one. Let x belongs to A closure. See, this one might be easy for most of you. But I am still solving this. Because I need this problem or I need this result for the next 1 or 2 problems. Okay. So now suppose x belongs to A closure, you have to prove that d of x comma A equals 0. Okay. So to prove this is equal to 0, what you have to prove? See, we say means if we are able to prove that, if we are able to prove d of x comma a is less than epsilon for any positive epsilon, right? Then we are done, right? So do the same thing. Let epsilon an element non-negative, right? Now x belongs to A closure implies this B of x comma epsilon intersection A is non-empty. I don't know. I am making the mistake always. So Bx comma epsilon intersection A is non-empty. Then set let an element y from here. Okay. Let an element y from here. So this will imply y belongs to A and y belongs to B of x comma epsilon. So this will imply d of x comma y is less than epsilon, right? Now see, we have an element in the in this set, means if we consider this as a set, your d of x comma a such that, so this is our A, this is a subset of A belongs to A, subset of R, right? We have this set and there exists an element dx comma y in A such that d of x comma y less than epsilon. Then what can we say about this set? What can we say about infimum of A? This is, or say it is A naught. This is not same A. Okay, what can we say about A naught?
0.
Yes, why 0 means we have
Because
not
sir
reached.
infimum भी less than epsilon होगा वो arbitrary है.
Yes.
हाँ, right. Infimum less than epsilon arbitrary है. So this implies infimum of A naught equal to 0, right? So that's mean d of x comma A equal to 0. Fine. Clear? Okay. Now this one. Huh. Now we'll prove some result from metric space, right? Yeah. So now what it's saying? A and B are two non-empty sets. This is problem number 3 from your book. Okay. So A and B are two non-empty subsets, and it is given that A closure intersection B is empty is equal to A intersection B closure. You have to prove that there exists two disjoint open set. Means if we have a metric space and A and B are two subsets, we cannot say, but A and B are two subsets which are disjoint, as well as if we take the closure. Okay, actually what we can say, no, not in this. Okay, so A and B are not only disjoint, but if we take if we take the closure of A, then its closure will also not contains no points, or will also contains no point from B, and similarly from B also, right? You have to prove that in this case, this A and B are also separated by means of open sets. Okay, this is given, right? Okay, now let me consider a function. So have you got the question? What does it ask?
Yes, sir.
Yes. So now you consider a function f from x to 0, 1 or from x to r. Okay, not 0, 1. And define this fx as d of x comma a minus d of x comma b, right? Consider this one, f of x equal to d of x comma a and d of x comma b. Then what can you say about when right now when x belongs to b, what can you say? X belongs to b implies d
dx
of x
equals
comma b equals to 0, right? And fx, so fx equal to d of x comma a, right? So can it be 0 d of x comma a?
No, sir.
Why?
Because that a bar intersection b equal to phi.
Yes, a bar intersection b equal to phi. Right, so this is not 0. Not only that, it is strictly positive, right? Because b closure intersection a equal to phi. No, not this one. Which one? A closure, right? A closure. We are using a closure here. A closure intersection b is equal to phi. And if you take an element x belongs to a, then this will imply d of x comma a equal to 0, right? But in that case, fx will be minus dx comma b, and this is non-zero, right? Because again here b bar intersection a is empty, right? Because no element, because x is in a, so x cannot be in b closure, and therefore it is non-zero by above result, right? Which we have just solved, that if this d of x comma a is equal to 0, if and only if x is an element from a closure, right? And so here fx is less than 0. Now what does this implies? The first one, see, x belongs to b implies fx less than 0. So can we say this b subset of f inverse, sorry, this is greater than 0, right? Sorry, this is greater than 0. B subset of f inverse, what? 0
0.
comma infinity, right? This is say our u, and x belongs to a implies fx less than 0, and this implies a subset of f inverse minus infinity comma 0. So our v, right? So b subset of u, a subset of v, and u intersection v is, this is what?
Empty.
Yeah, this is empty. So we have achieved our goal, right? So we need one two open sets u and v, where a contained in u and b contained in v, right? Huh. Now this one, can you prove? This is simple. Closed subset of a normal space is normal. So can you quickly tell me? So so why it is? Y closed in X. Okay. You have to prove that Y comma tau Y is normal. Right? So to prove normal, you have to take two elements, say A comma B, say closed in Y comma tau Y. Right? Then A equal to
A intersection
A
x.
intersection Y.
A equal to A intersection Y. Only A intersection Y. There will be, we first take some other set, right? Say A1 intersection Y, and B will be B1 intersection Y, where these A1 and B1 are closed in X, right? Now this is closed in X, this is closed in X, therefore this is closed in X. So A is closed in X. Also B is closed in X. Then now X is normal. Then what can we say?
There exists an open set U and V such that A is contained in U and V is contained in V such that U intersection V is empty.
I missed something. You also missed something. Tell me what? What we missed? Yes, yes, yes. Yes, yes. I cannot hear you. Can you please tell it again?
Sir, if A1 and B1 are disjoint, then the statement will true.
Yes. So we have to start with two disjoint sets, not only closed. Say closed in Y with A intersection B is equal to empty. Okay. These two are empty, and then we can say there exist open sets U and V in X such that U intersection V is empty and A subset of U, B subset of V. Now just take their intersection, or this is take your U1 to be U intersection OI and V1 to be V intersection OI. Open in. So from where? From tau y, right? You have to take tau y to prove the normality of this space y, or y comma tau y, right? Fine. Now this one. Oh, no, that missed. Yes, this one. So now first understand the question. Okay. So Ax, it is given that a normal space and A intersection B is equal to 5, right? You have to then from the definition of also A and B are closed. A comma B are closed. Right. Now you have to prove not only this one. So this is the definition of normal space, right? There exists open set A U and V or V and W such that A and B are separated by these two open sets, and these two open sets are disjoint. But this question tells you, asked you to find some, if it is a normal, then you can find some open sets V and W. Not only they are disjoint, not only they contain A and B, but also they are closure. If we take the closure, their closures also have the empty intersection. Right. So okay, let's try to find out. So A and B are disjoint closed, right? So then first apply the first definition. This implies there exist open sets, say U and V, such that U intersection V is empty and A contained in this. Right. Now you have this one. You see, V is open in X, right? Also, U is open in X. So U complement is closed. And also closed with, right? And one more thing, what else we can say? That U bar intersection V is empty and V bar intersection U is empty, right? Right? Now consider, yes. Now consider A and U complement, right? These both are,
Sir,
yes, yes.
सर ये कैसे है u bar intersection v equal to phi and v bar intersection u equal to phi?
Yes. Why? I'm not getting the
सर
question.
ये सर ये आपने कैसे लिखा u bar intersection v equal to phi?
हाँ,
कैसे लिखा?
कैसे
समझ
लिखा?
नहीं है।
अच्छा, this one, right? Now take x belongs to u, right? X belongs to u. Then u is a neighborhood of what? X, right?
Yes sir.
But this one, but u intersection v is equal to phi, right? So x has a neighborhood u which is disjoint from v. Can we say x belongs to v bar? X
No,
belongs
sir.
to V bar का मतलब क्या है? What do you mean by X is in the closure of V? Means for every open set of X or every neighborhood of X has a non-empty intersection with V.
Okay,
But
okay,
U
it's clear.
is a neighborhood of X which has empty intersection. So
Clear,
we
sir.
have this one. Clear? Huh. Right. So what I was doing, U and V. Huh. Now see this U. Look at this one. What I have to take. Now look at this one. Sorry. Look at this one. U bar intersection V is equal to phi, right? And this implies U bar intersection V is also phi because B is a subset of V. Now U bar is closed in X and B is also closed in X and X is normal. Clear? U bar is closed in X, B is closed in X, and U bar intersection B is empty and X is normal space. So then what can we say? There exist open sets U01 and V01 such that U bar contained in U1 and V bar contained in V1, right?
So B
Right?
contained in V1.
Yes. Sorry. So consolia U bar and B, right? This one. This B contained in V1. Thank you. Right. We also say something more. What? We also say that U1 bar intersection V1 is empty and U1 intersection V1 bar is empty, right? Now we will use whatever thing we need. Right? Right? Look at this one. Look at this one. U1 intersection V1 bar is empty and U bar contained in U1. Then what can we say from this one and this one? U bar intersection V1 bar is empty, right? Right?
Yes, sir.
Now अब देखो ये पहले ये कहां पे था? A was subset of U. Where it is? A was subset of U. Right? A was subset of U. अब यहाँ पे आ जाओ B subset of V1, right? B subset of V1 and U bar intersection V1 bar is equal to phi. Have we got the final result? There exists open set U and V1 such that A contained in U, B contained in V1 and their closures have the empty intersection. Fine. Fine. Is the converse true?
Yes, sir.
Is the converse true? Is the converse true? This is trivial, right? If this one holds, A subset of U, B subset of V1 and U bar intersection V1 bar is empty, then see this one U intersection V subset of U or U bar intersection V or U intersection V1 subset of U bar intersection V1 bar. Now this is empty, implies this is empty. So the converse is true, right? Okay. So is it clear? It's very
Yes.
interesting. We will see one more result, one more similar result, and sometimes this result also used as a definition of that normal space. Okay. So sometimes this is also used for definition of normal space, or somewhere people uses to use this result to prove that some space is normal. Okay, because here you have to deal with only one closed set and one open set containing it, or one closed set and one open set. So let's first prove the forward part. So what does the question says? Or you can treat it as a theorem. Okay. So a topological space is normal if and only if each closed set A and each open set V with a subset of V. So for each closed set A and open set V such that A subset of V, there exists an open set W. This W should be open. Yes, open set W such that A contains W closure contains V. Means if you have if you are in a topological space and if for each closed set A and each neighborhood or each open set containing it, you can find out another open set in between. If you can find out another open set in between, say W, whose closure is also contained in there, means if you can find out some open set in between between A and U, whose closure is also lies in U. In that case, we will say that the space is normal. See, it may you can you may feel that this is some non-trivial argument, or it may be difficult to you for the first time. But if you read this statement again and again, and if you then you will understand that what is going on here. So first prove that this is this whenever the forward part. So suppose, so let X is normal, okay, and this is not X be a normal space, and what, A be a closed subset, X, and take U X and U be open or V be open in X such that A subset of V, right? So then what can you say? What is V complement, or say V complement? This is closed, right? Right? Fine.
Yes, sir.
This is closed and A intersection V complement is empty, right? Now you apply the definition of normal space. So what does it say? It says that there exist open sets, say U1 and or say U and W, such that A subset of U and V complement subset of W, right? V complement subset of W, right? Now also again what we can say, this this W closure intersection U is empty, right? By the same argument, same previous argument, right?
Yes, sir.
Then and here also one thing, U intersection W is phi, right? Then what is that? Huh. Intersection U is fine. Fine. And so I want B complement here, right? Instead of U. So W bar intersection B complement. No, not this one. I want something else. Oh, sorry. Sorry. I did some mistake. We do not need this one. Yeah, look at this one. Now A subset of U, right? And also U closure intersection, this W is equal to phi. Right, U closure intersection W is equal to phi. And this implies U closure subset of W complement, right? Is it clear?
Yes, sir.
U
Yes,
closure
sir.
subset of and W complement subset of from here.
V.
Subset of V, right? So what we have, A by this one, A subset of U, U is subset of U closure, subset of P, right? Yes, we have A instead of W, we have got U here, okay? No matter, but this is still an open set. A subset of U closure, subset of V, right? See, A subset of W closure, subset of V. Okay. So we are done with the forward part. So what about the reverse one? Suppose this condition holds. So let X be a space with the property that whenever A is closed and U open set containing A, there exists some W for open set W such that A subset of W by subset of V, right? To prove that X is normal, right? To prove X is
Sir,
normal. Yes.
so it should be W closure subset of U because we have taken U open set.
Okay, okay, okay. Yes, yes. So this is U. Thank you. Yes, yes. Actually, I forgot the notations. That's why I lose many marks throughout my M.sc, my B.sc, and so on. Okay. Anyway, so this should be U, right? Now you see, so you have to prove that your space is normal. So let, as usual, A or say B and C be two disjoint closed sets. Right? That is B intersection C is empty. Then what we can say? This implies B subset of C complement, right? Yes. And this is open. B intersection C is empty implies B subset of C complement. And C complement is open because C is closed. Now B subset of C complement, and by this hypothesis, so this implies there exists some W open in X such that A subset of W closure subset of C complement, right? Now we have one open set W, so A subset of W, right? We need other open set. You see, W complement contains, sorry, W closure contains C complement. So then what can we say from here? C complement contained in W closure complement, right?
Yes, sir.
Huh. Now can we say W intersection W closure complement is empty? Wait, what is this? W closure. Yes, yes. So can we say this one?
Yes, sir.
So and we got the result, right? This is another open set. So C complement. So this is C contained in W closure complement. Done. Okay. Therefore, this space is normal. So whenever this condition holds, means if for each closed set A and each open set V with a subset of V, this result holds. You can find out some open set W which is lies in between, and those closures lies in like A and V. So lies between A and V, then the space is also normal. Fine. Okay. Now this one. Shall I prove this one? This is very big one. And I also want to prove that Moore space, and some of you have asked that Moore space is not completely regular. Sorry, Moore space is completely regular but not normal. I will prove this one at the end. Now, I have two problems. This one and this one. Okay. So tell me if some of you have some progress with this problem, means if you have solved or if you have some idea. So what this question says that we have a normal topological space X and A be a closed subset. Okay. So you have the question claims that if there exists a continuous function such that F inverse of this set, zero singleton set, is A, if and only if A is a G delta set. One way is obvious, right? Which one? And for this, we do not need that normal property or G delta set property. Sorry, we do not need the normal property of that space. So which one? So if A is equal to F inverse of 0, Then this is F inverse of what? Intersection n equal to 1 to infinity. Then what? 0, 1 by n, right? And this is same as intersection n equal to 1 to infinity F inverse of 0, 1 by n. And those are open sets. And this is the countable intersection of open sets. So we have written so A as countable intersection of open sets. So it's a G delta set. Now let's write conversely. So let A be a G delta set. Right. So G delta set means A equal to countable intersection of open sets, right? Say Vi or Vn, or say A equal to intersection of Un. Erase this one. This is A equal to n equal to 1 to infinity, right? Where Un are open sets. Right? Yes. So we have to find out a continuous function. We have to construct a continuous function. Right. Now see, A is the intersection of all those. So if we consider, so Un complement, it is a closed set, right? And Un complement intersection A is empty, right? For all n. Clear? Please respond.
Yes.
Actually, this problem is not that much trivial, and in the next problem we will use these results. Okay, so please respond and understand. So, and whenever you do not understand something, please stop me and ask. Otherwise, you will not get the entire thing, or your class will be, there is no meaning will of for you, means this time will be a waste. Okay, so this one. Now this is equal to phi. Can you remember Euryson lemma? Euryson lemma? Anyone? Yes. What is the statement?
F a space is normal if and only if there exists a continuous function
A
that
space is normal if and only if,
if
then
continuous separation of closed sets.
yes, we can separate to disjoint closed set in by means of continuous function, right? Only for disjoint closed set A and B, there exists a continuous function f from x to 0, 1 such that if A is equal to 0 and if B equal to 1, right? This is the Euryson lemma. Now we have a normal space X. X is a normal space. Is it if and only if condition? Let me check. I think so, but let me verify it once again. Lebesgue number lemma. Separation axiom. Is it if and only if condition?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Actually, in my book, I can see the only if condition. Like if normal space implies for disjoint, means normal space implies disjoint spaces are separated by continuous function. Let me check it on a printer's book. Actually, I want to verify this one. Bootstrap locally compact bits extension. This following are equivalent: normal space and closed subset, continuous function, continuous extension, pair of disjoint closed sets. Yes, pair of disjoint closed sets can be separated by continuous function. Yes, yes, it is if and only if condition. In some book they miss something. Where is the pen? Yes. Right. So now you have you have two disjoint of closed sets un complement and a in a normal space. So by Eurytion lemma, what you can say? You can say by Eurytion lemma. Let me use different color. Lemma. There exists a continuous function if, let me write it as index fn from x to 0 1 such that fn of a is equal to 0. Let me write it precisely. Fn of x is equal to 0 for all x belongs to a, right? All x belongs to a, and fn of x equal to 1 for all x belongs to Pn. And this result holds for all n, right? Right? Now you see that all these are continuous functions. Now we consider another one. Now tell me, now recall something from your real analysis course. Okay. So consider this function n equal to 1 to infinity 1 by 2 to the power n fn x. This is a series of function, right? This is a series of function, right? Can you remember Wester's M test, or can you please tell me whether this series is uniformly convergent? Can you say that? This series is uniformly convergent. Verify. Okay. Wester's WIERS Wester's M test. I am giving you the name. Wester's M test series is uniformly convergent, and say let fx be the sum. N equal to 1 to infinity 1 by 2 to the power n fn x. Okay. So this is, says suppose this our fx is the sum. Then f is continuous, right? F is continuous. Sum of a uniformly convergent series. The sum function. If each term is continuous, then this f has to be continuous, right? Fine? Yes. Have you forgot all those? Are you getting this one?
Yes, sir.
Please follow this one. If you are not getting, please ask. Okay. Anyway, so now this f is continuous. Now what is our aim? We have got a continuous function. If we can prove that this f inverse of 0 is equal to a, we are done. Right? So now one thing is, if x belongs to a, then what we can say? Fx. Then fx will be, which is sum of n equal to 1 to infinity fn x, right? But for x belongs to a, each of fn x is 0 by the hypothesis, right? We have constructed this function. We have constructed this function fn in such a way that fn x is equal to 0 whenever x belongs to a. So, and therefore, whenever we have taken an element a, each term of this, sorry, 1 by 2 to the power n term will be there. Each term of the series is 0. Therefore, fx is 0. But fx x belongs to a implies fx equal to 0 does not mean that f inverse of 0 is equal to a. We have to prove the reverse one also, right? So now suppose this one implies only the reverse inclusion holds. Now suppose some x belongs to here, means f inverse 0 means suppose fx equal to 0. Now fx equal to 0, what does it mean?
Summation 0.
Yes, summation 0. Summation of fn x 1 by 2 to the power n equal to 1 to infinity. This is 0, right? This summation. Now look at the each term of the function. See, each fn x is
Positive.
non-negative, right? Not positive, it is non-negative.
Yes, sir.
Non-negative, right? Now, to since to for the summation to be 0, we need each term has to be 0, right? Because if there are some n naught which is non-zero, then this summation will be non-zero. So this implies that each of fn x is equal to 0 for all n, right? And this is equal to 0, and so this implies since fn x is equal to 0, now come to here. Fn x is equal to 1 whenever x belongs to Vn. But we have got fn x is equal to 0. See, here I have taken fn x equal to 0 whenever x belongs to A. I did not say that fn x is equal to 0 only if x belongs to A. Means there may exist some y in x minus A such that f y is equal to 0. Okay. This means this one. Now see, here each fn x is equal to 0, but for each x in V, we have fn x is equal to 1. Then what can we say from this two argument? X cannot be in Vn complement, right? Oh, I have given here Vn. Sorry, I did a mistake. This should be, I've taken again Vn.
UN.
Yeah, this should be Un complement, right? You should tell me because I did a lot of notational mistake. Okay. This UN complement, and so this function will again be UN complement, right? Because this is the Eurytion's lemma. Whenever we have two closed sets UN complement and A, which are disjoint, we can separate by this continuous function Fn, right? Now come to here. Fn x is equal to 0. So Fn x is equal to 0 implies x does not belongs to here again UN complement, right? Because when x is in UN complement, then Fn x is 1, right? So this implies x belongs to UN for all n belongs to n, right? And this holds for all n. This means x belongs to intersection 1 to infinity UN. And what is the intersection? This is
A.
This is
A.
A. This is A. By this assumption, right? Which one? By this assumption. By this assumption. We have taken A as a G delta set where each open sets are of this form, right? So X belongs to A, and so this implies what? We have taken an element. This means X belongs to F inverse of 0. So we have got that F inverse of 0 subset of A. Earlier we got A subset of F inverse of A, this one. A subset of F inverse of A, 0. Therefore, F inverse of 0 is equal to A. This is the result. Okay, clear? Tell me if it is not clear.
Yes, sir. Clear.
Okay, fine. Okay, and then what about B? This portion, the second term. G delta set, and this is a closed set satisfying. Actually, this second one will also follow the similar kind of things. But there at some stage, since we are having two disjoint sets, at first I am giving the idea. Okay, I am not proving this one. I'm just giving the idea. Sorry, the same idea will work, but initially you have to start with this from. So, okay, let's first read the statement that if A is a G delta set and B is another closed set. So, given A is G delta, but B is a simple closed set. It need not be closed. Or A is closed set is given in the first one. Okay, so A and B are closed sets where A is a G delta set. Okay, with their their intersection is empty, means A and B are disjoint sets. In that case, there exists a continuous function. You can find out a continuous function G such that G inverse 0 is equal to A and GB is equal to 1 for each B belongs to B. See, G inverse 0 is equal to A is similar to this one. F inverse 0 is equal to, sorry, this will be this one. F inverse of 0 equal to A. But GB equal to 1 is something different, right? GB is equal to 1 for each B belongs to B. So, okay. Yes, clear? So please understand the statement first, and then I will give you the sketch. You can prove it by yourself. I will prove the next problem, and then I will prove this one. Maybe we will continue till 5 o'clock because you have the exam, and I want to finish that problem. That Moore plane is completely regular, but not normal. Okay. Actually, here we are given two space. Here is B, two space A and B closed, and where A intersection B is empty, also given that A is a G delta set. Okay, and you have to find out some G from X to 0, 1 such that G inverse of 0, 0 is equal to A, and but G of B is equal to 1 for all B belongs to B. Means there can be some other points in X, or there can be some other point outside of B whose image is 1 under the map G. Okay. So what we will do is that you first separate these two closed sets by in terms of open sets. Means there exist closed sets U and V such that A subset of U, B subset of V, and U intersection V is empty. Okay, this is the first argument you do. Then you take, since A is a G delta set, you take A as intersection of open sets. Okay, say it is Vi or Vn, right? These Vn's are open in X. So Vn's are open in x, right? But see, these Vn's are open, but these Vn's can have intersection with B. These Vn's can have intersection with this V. But if we take this A as intersection n equal to 1 to infinity, Vn intersection V or Vn intersection U, then this will also work, right? We can write this set A as this intersection. But you see, if you give each element as name as ui, then ui intersection this V is empty. Clear? Actually here I am taking A as a countable intersection of open sets. But for this problem, for this particular problem, I want these open sets A which is intersection of open sets. These open sets are disjoint from this open set or disjoint from B, and then only we can produce such a function G. So now by this argument you find some open sets ui which are disjoint, and then write A as intersection I equal to 1 to infinity ui. Okay, and then apply the previous argument, this ui, then apply the take ui complement and A. You can find out some functions fn or fi, or say this is as n, it as n. You can find out functions fn, then consider g as summation n equal to 1 to infinity 1 by 2 to the power n fn. Okay, consider this function. You will see that this function will give you this result. Okay, is it clear? Actually you have to do the same thing, but the extra thing is this one. You have to find out you have to write A as intersection of open sets, each of which are disjoint from B. That is the trick, and rest are similar to the previous one. Okay, this is an exercise. I have given the sketch. Please ask me, please tell me if it is not clear. I will explain again. See, you can expect this kind of question in the exam. I don't know, as are given in the class, and he also mentioned the question number 7 several times, as I remember. Okay, clear? Shall I move to the next problem? If it is clear. Are you here?
Yes, sir.
So can I move to the next problem?
Yes.
Yes, sir.
Yes, sir.
Okay, fine. This is just application of the previous one. Perfectly normal. So perfectly normal. This is the one we use here. Oh, okay, not this one. Okay. Okay, so first we prove that perfectly normal implies every closed set is G delta set. Now let us this blue color X be a perfectly normal and Hausdorff and T2 space. Okay, this one. So this perfect normal and T2 space. Now take every closed set is a G delta set, right? Now take a closed set in X and take an element from X minus A, right? Then T2 space implies this singleton, T2 implies T1, right? And T1 implies, this implies T1 and T1 implies this is
Closed.
closed. Yes, this is closed. Now we have A and B closed subset, right? Closed subsets of X, right? Now we assume that X be a perfectly normal space. We have two closed subsets A and this A. It's not B. This is this A singleton set. Okay, we have perfectly normal space. By definition, there exists a by definition continuous function f from x to 0, 1 such that what? Such that, so please understand the definition of perfectly normal. Perfectly normal means if you take two disjoint sets A and B, then you can find out the continuous function f such that A is precisely the inverse image of the singleton set 0 and B is the inverse image of singleton set 1. This is different from fa equal to 0 for all A belongs to A. Okay, this is a subclass. So sorry, this is which one? So whenever this happens, A equal to f inverse 0, then this is automatically happens. Means this is a subclass of this one. This one is a bigger class. But I am taking, but in the definition says this is precisely A is equal to f inverse 0. Okay. You can find out a function and B equal to f inverse 1. Okay. This is the definition. A perfectly normal space. So now we have a perfectly normal space, and so by definition, and two closed sets A and A singleton set, we can say there is a function such that f inverse of 0 is A and f inverse of 1 is A singleton set. Therefore we are done, right? Because we were needed this one. So Hausdorff space perfectly normal implies, so this implies A is equal to f inverse of 0. Now come to here, come to this problem. As I told you, I will use this problem. See, for a closed subset A topological space, if there exists a continuous function f such that f inverse of 0 is equal to A, then A is a G delta set. So our this function satisfies the hypothesis of the last result. A is equal to f inverse 0. F is a continuous function in a topological space and A is a closed. So this implies A is a G delta set. Clear? Okay.
Yes, sir.
Let's prove the reverse one. This is easy. Means okay. So we assume the every closed set is a G delta set, and we will use the second argument of the last problem. Now let A and B, let me solve it quickly by 2 minutes. A and B be closed subsets such that A intersection B is empty, right? And also what? We assume that A and B are G delta set because we assume that every closed set is G delta set. Also A and B these are G delta sets. Okay. Fine. Now since A is a G delta set, and B is closed, there exists G from x to 0, 1 such that G inverse of 0 is equal to A and GB equal to 1 for all B belongs to B by
Second part.
yes, by second part, by this result. Okay, by this there exist functions G inverse 0 is equal to A and GB is equal to 1, and similarly we apply the fact that A is a G delta set. Also B is a G delta set and A is closed with A intersection B is empty with A intersection B is empty, right? So this will imply there exists some function say k from x to 0, 1 such that k inverse of 0 is equal to B and k of A equal to 1 for all A belongs to A, right? We got two functions, but we want a single one. Now consider a function f from x to 0, 1 by fx is equal to half of, let me use different color so that you can remember. Fx equal to half of gx plus 1 minus kx. Okay, consider this function and verify the rest. Okay, this is rest of the things are easy. You have to prove that the verify I am giving here. Okay, verify f inverse of 0 equals to A and f inverse of 1 is equal to B. Okay, please verify this one. Is for you. Verify the rest. Okay, so this will be those are very easy. So verify the fine. Okay, clear. See now we have got a function. Now you can do it easily. Okay, fine. Shall I move to the last problem? Or
Yes, sir.
okay, okay.
Yes, sir.
I think I took too much time. It's 1 hour and 25 minutes now. Oh, he did something. Constructability. Don't know what to use. Take clear kitchen, teams and demos. Let me work on it because he did something, but okay, let me save this one. Actually, I want real 5. Okay, so let me just cross this one. Just use the space, okay? This one and this one also. Actually, some of my friend did something on that whiteboard, but I do not want to erase that one. Maybe that is useful for him. And I have created only this that much, and I have replied and I prepared that problem only after. Okay, let me write down the question. Moore space is completely regular. Fine. So what is the definition? Completely regular means given a closed set X and closed set A and X belongs to X minus A, right? There exists a continuous function f from x to 0, 1. Let me write it as 0, 1 such that fx equal to 1 or fx equal to 0 and fa is equal to 1 for all a belongs to a. This one, right? This is the definition of completely regular space. Now we claim that Moore space is not completely regular. Okay. Now take X belongs to M, where M denotes the Moore space, and I assume that you all know the definition of Moore space, right? So X belongs to M, and let U be a neighborhood of M, or sorry, X. Let me write it precisely. That is that X belongs to M and A be a closed subset of M disjoint from X. Okay, this is disjoint from X. Now since A is closed and X does not belongs to A, so this implies there exists an open set say U in X such that X belongs to U, but U intersection A is empty, right? That is a subset of U complement. Now we want to define a function f such that f continuous function f on Moore's plane such that fx is equal to U in M. Let me So fx is equal to 1 in fx equal to 0 in x, fx equal to 1 in u complete in a, which is continuous. Now let us define the function. Now define a from say m to 0 1. How? F of x is equal to 0 and f of x equal to 1 for all x belongs to m minus u. Means, let me give you the picture. So suppose this is your space, this is the upper one. You have a point either here u, this is your neighborhood u. Okay, and as I said, a is disjoint from you. This a will be somewhere here. Okay, this can be one possibility, and other possibility can be your other possibilities can be your points. X is in here, right? Then u neighborhood will be of this form, and your A set is somewhere here. Okay, this is your A set, right? Now we want to define a continuous function. We have defined fx is equal to 0 at the point x. This is our x, and for this picture this is our x. Okay, fx is equal to 0, and outside in these spaces we have defined f of x is equal to 1, right? You see, if we consider the boundary, what is the value of f on the boundary? For x belongs to boundary of u, what is the value?
According to definition, it should be 1, sir.
Yes, according to definition, it should be 1 because u is an open set, right? So fx is
Yes.
equal to 1, right? Now, suppose you have a point here. This green color is. So you have a point here, and at this point your functional value is 1, and outside also functional values are 1. But we have defined also the functional value at x. We are yet to define the functional value on u except the point x, right? Now you have x here, you have some, draw a line from x to this boundary. From x to say it is y, y is a boundary point. Here you have x, and draw the line in the boundary and define. So if you draw a line in the boundary, say if your x is say x comma, sorry, let me come here. If your x is x1 comma y1, and if it is y is x2 comma y2, then what will be the points in between? Means if you consider the line x to y, what are the points? Points are you have to,
Lambda x plus 1 minus lambda y.
yes, lambda x. Let me start from the 0. Okay, let me write lambda of y plus 1 minus lambda of x. This will be a typical point in the line 0 less than equal to lambda less than equal to 1. This is the line, right? So if you consider this is your x, this is your y, so this will be the line, and any point in the line will have this form, right? Now you define a function Now you define the, so this is suppose a typical point, say alpha in the line. You define f alpha, alpha belongs to u, f alpha to be lambda of fy. Oh, so then it should be lambda of fy plus 1 minus lambda of fx, right? Right? So what is lambda fy? 1, right? According to
1.
definition.
Yes, sir.
Or what is fx? It is 0.
Yes, sir.
This is lambda. Now define your f alpha to be that lambda. Okay, that is the distance from x to the point alpha. So if this is your point alpha, you define it as alpha, and by this argument you feel the functional value on u. This kind of extension is called a linear extension. Okay, you have some functional value here, you have some functional value there, and you are defining elsewhere by linearly, means you are extending f linearly, or simply you can say that now extend f linearly. Okay, you will see that this f is continuous. Why it is so? Again we will use something which we know. Do you know the Pasting lemma? I taught you during the tutorial, and I told you it will be very useful during problem solving sessions or whenever you solve problems. So yes, now tell me one thing. If you have a linear function in a if you are in a linear space, if you have a linear function, is it continuous?
Yes,
Yes,
sir.
a linear function is continuous. So what we can say, f is a linear function in U closure, right? Means U union its boundary, right? U closure is closed. U with its boundary, right? And then what? So if is, so this implies f is continuous. On the other hand, fx equal to 0 in the complement of u means 0 for x belongs to m minus u, right? Fine. Sorry, this is 1.
Yes, it's 1.
1, right? So mean therefore fx is also continuous outside. Now see. So say this is our B, say this is our A, right? So A is a closed set. Is it a closed set?
Yes, sir.
Yes, it is a closed set. This is closed. What about this one? B? B is
Close.
closed. A comma B closed sets. Right? And now, and both F and F is continuous in both A and B. Fine. Now you see A intersection B. In A intersection B, what is the value of F? For x belongs to x, what is the value of F? Fx is equal to?
1.
Yes, F is equal to 1. Fine. So can we apply Pasting lemma now?
Yes, sir.
Why? Why? What will be your G? You have some G, you have some H, and in the intersection they have the same values. Say you can consider your G as F restricted to A. You can consider your H as F restricted to B. Then if the restriction function in this common interval, or sorry, in this common intersection, they have the same value. Therefore, F is continuous, right? By Pasting lemma. By Pasting lemma, F is continuous. Okay, F is continuous. So we're done, right? because fx is equal to 0. See, I wrote x everywhere, and also I have fixed my x. So please do not be confused about that, right? So let me write this one as y, or this one as z, this one as z. Okay. So, but continuous now, f of x is equal to 0 and f of a equal to 1 for all a belongs to a. Why? Sorry, f of a equal to 1 for all a belongs to u complement, right? But our a was a subset of u complement. You see where it is? This one, u intersection a is equal to 5. So this implies a subset of u complement, right? But in u complement, the functional value is 1. Fine? Clear? Yes, please respond.
Yes,
Yes,
sir.
sir.
Yes. Please be response and be confident. So a subset of u complement and functional value is 1 in u complement. Therefore, fx is equal to 1, or say fz is equal to 1, or f of a is equal to 1 for all a belongs to a as a subset of u complement. Fine. So we have proved that the Moore space is completely regular. Now we are trying to prove that Moore space is not normal. Moore space is not normal. Right? So what is the definition of normal? Now tell me Tietze extension theorem. So you all know the definition of normal. Tell me Tietze extension theorem. Tietze extension theorem. Tell me this one. So what is Tietze extension theorem? Yes. I remember, but I should confirm it from your book before I give you this one. Hey, look, why does locally compact kind of things comes? We want justice. We want Tietze. I can yes. Closed subset of a normal space, and if you can define what it is. If we have a continuous function, there exists a continuous extension. So let say OI be a closed subset of a normal space. Okay. Then any function, and let f from OI to which codomain you want to take. So it is
R.
a 0 R. Okay, R. This be continuous. Then there exists a continuous function f hat from x to R such that f hat restricted to y is equal to f. Okay. This is the definition of Tietze extension theorem. We will use this one to prove that the Moore space is not normal. So here the normal space is important. So this is important. Okay. Normal space. This holds only in normal space. We'll prove that we can find out some functions which cannot be extended in Moore space, and therefore it is not normal. We will use this argument. Okay. tell me one thing. If you consider this set, so suppose you consider this set, y is equal to p comma q such that p comma q belongs to q. So this, of course, this belongs to M. Okay, mood space. So this is a subset of M. Okay, this is a countable set, right? Is it?
Yes.
Yes, sir.
Yes. So this is a countable set, and also this is dense in M, right? Y is dense in M. Fine.
Yes, sir.
Clear? Huh. So now, if f from M to R is continuous, then this continuous function should also be continuous in Y, right? This implies f is also continuous in Y, right? Now let us try to find out the number of functions. So how many functions are there in okay. So how many function you can, this is not only continuous, so the number of function from Y to R. So how many function you can define from Y to R? What is the number? Cardinality? What is the cardinality of Y? Countable cardinality, right? This is LF naught. Right? What is the cardinality of R? This is C, uncountable. And therefore the number of function from Y to R is C power LF naught. And this is again C. Clear? This is from continuum hypothesis. I'm also using those. If you ask me to prove those, I forgot the proof, but just remember this one, that this is this is the countable cardinality, this is the uncountable, and C power LF naught is again C. Fine. So therefore, number of function from Y to R is this one. Therefore, number of continuous function will be at most C on. So therefore number of continuous function, this is the total number of function, and out of those some of the functions are continuous, because not all functions are continuous. Number of continuous function on Y is at most what? C, right?
Yes, sir.
Yes.
Yes. Now each continuous function on Moore's plane is also continuous in Y. Therefore, number of continuous function in M is at most C, right? This is one argument. So far, I have not used anything from normalness or anything on the hypothesis or anything from the topology. I have just used that if we have a Moore's, sorry, I have just used that once we have a Moore's plane, if we have a continuous function, then what is the maximum number of continuous function one can define in Moore plane, right? This is C. Now let's come to the second one. You consider this set Z as x comma y such that y equal to 0. Mainly this one. So if this is your Moore plane, we are considering the x-axis. So this has discrete topology, right? It has discrete topology, first of all. Fine? Clear? Because each set, if you consider the subspace topology z, tau z, each singleton set are open. Fine?
Yes, sir.
Huh. Now this has discrete topology. Second thing is Z is closed in M, right? This set is closed in M. Why? Because if this is your Moore plane, and if you consider an element outside of this line, means if you consider an element from here, then this element has a neighborhood disjoint from this line. Therefore, this cannot be in the closure of the line. Therefore, the line is closed set. So Z is a closed set in M. Now, so now Z has a discrete topology and Z is closed subset. Now you see, if we consider a function Z to R, any what can we say about that function? What can we say about the continuity of that function?
Every function is continuous.
Then if we consider any function f, then f is continuous, right? Any, because every function of f is continuous. Now how many function? How, see, now what is the cardinality of z? This is cardinality of R, right? Because this is
Yes.
nothing but this line, and this is again C. And now number of functions. So how many such function we can define? The number of function from R to R is C power C, right? This is, you can say, as 2 power C. Same. These numbers are same. 3 power C and 2 power C. These two are same. These comes from the continuum hypothesis, right? So 2 power C, and what you know, that you also know this C is strictly less than 2 power C, right? From the set theory, from the continuum hypothesis, right? So C less than 2 power C. Now you come to here. What does Titze extension theorem says? It says that if our Moore plane is continuous, sorry, Moore plane is normal, if normal space say X, let me write, if our Moore's plane X is normal and we have Z a closed subset, then any continuous function can be extended to a continuous function of X. Fine. This is one argument. Also, since we have C power C number of, or 2 power C number of distinct functions, so if we extend this function to Moore plane, that function should be distinct. That's mean we have the number of continuous function in Moore's plane is at least 2 power C, right? So this argument by Titze extension theorem, let me write it precisely. By Titze extension theorem, Titze extension theorem, each of f from which are z to r has a continuous extension in whole M, which are distinct, right? Therefore, the number of distinct continuous function in M is at least 2 power C. But what we got here in 1, the number of continuous function can be at most C. But we have C less than, strictly less than 2 power C by continuum hypothesis, and the number of continuous function in M, if this is normal, then it should be at least 2 power C. So we get a contradiction, right? Clear? Therefore, we get a contradiction. Contradiction to 1. Clear? So M is not normal. Clear?
Yes, sir.
Yes, sir.
Is it fine now? Tell me
Yes.
if somewhere you have any problems. Actually, I could have used this instead of using this TJ kind of things. I could have used this on just a definition of normal. Normal means it's not normal by taking two disjoint sets. But in that case, I need the application of Bayer category theorem. But in the the sir taught you the Bayer-Category theorem in last class, and I also read those in maybe 2 or 3 years ago. So I have to prepare this Bayer-Category theorem again before give something to you from the Bayer-Category theorem. Okay, and Bayer space. That's why I did not present the proof from the Bayer-Category using Bayer-Category theorem. I have used here Titze extension theorem here. Okay. If you want, you can also use Bayer category theorem argument to prove this. Just taking, say I have taken here, I have given the sketch of another proof. Just take, you have Z a closed subset, closed set in M. Now also Z has discrete topology. So if you consider the rational numbers on R, if Q be the set of or Q1, we cannot say Q here, Q1 be the Q1 is the element, Q1 equal to X comma 0 belongs to Z such that X belongs to Q, and if we say Q2 is equal to X comma 0 belongs to Z such that X belongs to Q complement or or R minus Q, that it is R minus Q. Then these two will be closed set in Z, and since Z is closed in M, so these two are closed in M, and Q1 intersection Q2 is empty. But using Bayer category theorem, you can prove that this there cannot you cannot find out to disjoint open sets separating these two closed sets. Okay, so this needs the argument from Bayer category theorem, but at this moment I will not give that because I also need some clarification from there before I present it in front of you. So that's all for the day, and please try if you can using by using just simple definition of uh, uh, not normal space instead of using Titze extension theorem. Okay. Okay, fine. That's all. I should write this tutorial. A. Okay. Or should I write it as more colors? Oh, it is complete. I again is completely regulars. Okay. Okay, maybe we can finish the session. Right.